Hi folks, we're going to take a look at number 4 from the Unit 2 assignment extra questions. So here they're giving us an exponential model to use, but we want to use a natural exponential model, so that means base e. So what I'm going to be working here is something of the form p equals p naught e to the kt. Okay, so let's take a look at what they give us. So the value of this 1924 gold medal is now worth, meaning at this point in time, so into 2018, it's worth $21,350. Okay, it's expected to increase in value at a rate of 4.5% every 3 years. Okay, and we want to estimate its value 10 years from now and how fast it's growing 10 years from now. Okay, so first thing to do is to find our model. Okay, and finding our model means we have to determine the k value because we already know that the base has to be equal to e. Okay, so what's going on here is that every 3 years the value increases at 4.5%. Okay, now you're going to notice that I'm going to do this question without specifically using this initial value. If you did, that's perfectly fine. But as we've seen, you don't need to know what the initial value is. I just need to know that after 3 years, the initial value will be 4.5% higher. So if I multiply the initial value by 1.045, that's going to be the value after 3 years. Okay, so it's p naught equals k times 3. It takes 3 years for this to occur. The reason why I didn't need the actual initial value in this problem is that when we divide that out to both sides, well, we see that the p naughts just disappear from the equation. So I'm left with solving this equation here, which is nice and easy because I just take ln of both sides. And here, the natural logarithm of e to the 3k, since the natural log and e to the x are inverses of each other, is just going to give me 3k. So k is just equal to ln of 1.045 divided by 3. Okay, and I'm going to estimate that. So let's figure out. So let's try to get so we can see. So ln of 1.045 divided by 3. So I'll take 4 numbers, so 0.01467. So I'll take 0.01467. So since we're dealing with exponential functions, I want to take a fair number of decimal places. Okay, so now our model is p equals p naught times e to the 0.01467 t. Okay, so this is our model. Now we can start answering the questions. So let's look at question 8. It says estimate its values 10 years from now. Well, nice and easy. Just stick t equals 10. So p is equal to, and now I do need the actual initial value of 21,350. So that's the value now, times e to the 0.01467 times 10 years. Okay, so let's calculate that here. So we've got 21,350 times e to these 0.01467 times 10, and looks like we have 24,723.44. Okay, so that's the value of this metal in 2028, or at least the estimated value of this metal. Okay, so now let's look at B. So B says, how fast is the value growing 10 years from now? Okay, well, this is not very calculus language, so we need to turn this into calculus language. So how fast is the value growing? Growing represents rate of change because it's how quickly it's growing. So essentially what we're looking for is the rate of change of the value 10 years from now. In other words, the derivative. Okay, so we need to take the derivative of our model and then from there determine its value after 10 years. Okay. Now, instead of working with this here, I just want to show you how, it gives you another one of the reasons why these natural exponential models are so nice. Because if I take any natural exponential model, okay, it'll save me some writing. And if I take the derivative of this, okay, let's take a look. P naught is just a constant. Whatever it is, it's just a constant. So I can take that out of the derivative. So I'm just finding the derivative of e to the kt. So here I need to use the chain rule because that's more than just t. So this becomes my u. So what's the derivative of e to the u? Just e to the u. So e to the kt. And what is the derivative of k times t? Well, t is my variable, k is just a constant. Okay, so it's just going to be times k. So the derivative of a natural exponential model is just k times p naught e to the kt. Okay? Now, I think if you think about what would happen if you found the second derivative, sorry, that's the derivative, second derivative, you'd see something very nice happen. So this hopefully gives you an idea as to why working with a natural exponential model is very nice. The only other constants I have is the k and the p naught, and here the k up there. I don't have any ln of other things that I have to deal with. But in this case here, I want to find p naught at 10. Okay, so it's just equal to 0.01467 times p naught, which is 21,350, times e to the k, 0.01467, times, in this case here, 10. But do you notice that this is exactly what I found earlier for the value? The only thing I have to do is multiply by the k value. Okay, hopefully you're starting to see why these models are so nice. Because once I have the value of the function, looks like I just have to multiply by k to get its derivative at that point. And luckily I kept that on my calculator, because that's what this whole expression represents. I just have to multiply it by 0.01467. Okay, and here we get about 362.69. Okay, so notice here, though, this is not dollars, okay, because it's how fast is the value growing. Well, it's growing at $362.69 per year, okay? So this gives us the rate of change. So after 10 years, it's increasing at a rate of almost $363 per year. Okay, so just a quick recap. This is what a natural exponential model looks like. Your first task is to determine what the k value is based on the scenario given. In this case here, in 3 years, it went up by 4.5%. Solve for k. Once you have your model, you can then determine whatever it is they're asking you to determine. Okay, and in B, had you actually inputted all these values in and then found the derivative, you would have gotten to the exact same.